Good evening. This is Mrs. Boland from the University of West Florida. I'm finishing up the lecture for Mod 7, which is confidence intervals. Tonight we're going to be discussing confidence intervals about the difference of means as well as the difference of proportions. First, let's talk about the means. Independent versus dependent samples. Two samples drawn from two populations are independent if the selection of one sample from one population does not affect the selection of the second sample from the second population. Okay, so independent samples means that simply put, that when you draw a random sample from one population, it has no effect at all on the random sample drawn from the second population. If that's not the case, otherwise, the samples are dependent. So we either have dependent or independent samples. Those are our only two options. Let's talk about an example. Suppose we want to estimate the differences between the mean salaries of all male and all female executives. To do so, we draw two samples, one from the population of all male executives and another from the population of female executives. So now we have two populations we're pulling from. These two samples are independent because they are drawn from two different populations and the samples have no effect on each other. Okay, so this is an example of two independent samples that are being drawn. Let's consider one that would be dependent. Suppose we want to estimate the differences between the mean weights of all participants before and after a weight loss program. To accomplish this, suppose we take a sample of 40 people and measure their weights before and then again after the completion of the program. Note that these two samples include the same exact participants. This is an example of two dependent samples. Such samples are called paired or matched samples. And the reason that they're paired or matched is because your beginning weight, your before weight, okay, must be matched with the after weight for each person, okay? Because that's the only way we're going to get an accurate difference of whether a person gained weight, lost weight, or their weight remained the same during the entire study. So we have to pair or match each sample up in order to take and determine the differences. Some of the notation that we need to know before we can take and conduct confidence intervals of differences. Okay, first we need to recognize that we have a population mean, and we're going to have a mean or mu from population 1. We're going to have a mean or population mean from population 2. We're going to have a standard deviation for population 1. We're going to have a standard deviation for population 2. We're going to have a sample size from population 1, and we're going to have a sample size from population 2. Sometimes we don't end up with the exact same sample size for both population 1 and population 2. Then we have an X bar, meaning a sample mean. That's from population 1, and we have a sample mean from population 2. So, and of course, if we did not have a population standard deviation from population 1 or population standard deviation from population 2, we would use S, our sample statistic, our sample standard deviation, to estimate the population standard deviation. Okay, confidence intervals for the difference of mu1 minus mu2. So to calculate a 1 minus alpha percent, so like a 95%, so alpha would be 5%, 1 minus 5, okay? A confidence interval for the difference of mu1, mu2 is calculated as follows. Here is your point estimate right here. Your point estimate is x bar 1 minus x bar 2. So your point estimate is x bar 1 minus x bar 2. Then you're going to add and subtract from your point estimate your critical value, z, okay, multiplied by the standard deviation about the difference of the means. And how do I calculate the standard deviation about the difference of the means? It's right here. It's this formula right here. It's going to be the square root of the population standard deviation of population 1 squared, also called the variance, divided by the sample size of population 1. We're going to add to it the variance squared of population 2, and then divide it by the sample size of population 2. And again, z is obtained from the normal distribution table given the confidence level that we determined that we want to calculate. If we do not have sigma 1 and sigma 2, and we have to take and use a sample standard deviation, in that case we're going to be on a different distribution. It's going to be the t distribution. And here's the formula for the confidence interval about the mean, the difference of the means rather, when we do not know our population standard deviation. Again, our point estimate is going to be the difference of x bar 1 minus x bar 2. That's the point estimate, the difference. We're going to add and subtract. We subtract to get the lower bound. We add to get the upper bound. Our critical value t, and then multiply that by the sample standard deviation about the difference of the means. And again, this is when our population standard deviation is unknown. So the sample standard deviation about the mean is going to be equal to the square root of the variance from population 1 divided by the sample size of population 1. We're going to add to that the variance of population 2, and we're going to divide that by the sample size for population 2. T is obtained from the t distribution, and the degrees of freedom that we will use is the smaller of n1 minus 1 or n2 minus 1, whichever one is smaller. Okay, that's how we're going to use the degrees of freedom. So pause the video if need be and make sure you have these written down, and make sure you know how to look at your UWF formula sheet to understand where all the different parts and pieces are coming from. Here's our first problem. According to the Bureau Labor Statistics, in 1993, construction workers earned an average of $551 per week. This was for construction workers. And manufacturing workers earned on average $487 per week. Assume these mean earnings have been calculated for the samples of 500 and 700 workers, respectively, taken from the two populations. Further assume that the standard deviation of weekly earnings, so that the standard deviation of weekly earnings for the two populations are $66 and $60, respectively. What is the point estimate for mu1 minus mu2? That's the first question we need to answer. So let's write down everything that we learned. What we know is that x bar sub 1 is equal to $551. We know that x bar sub 2 is equal to $487 right here. We know that our sample size for population 1 is 500, sample size rather for population 2 is 700 workers. We also know that we have population standard deviation. We know that we have the standard deviation for two populations, so this is sigma. We know that we have sigma sub 1 is equal to 66, and we know that we have sigma sub 2 is equal to $60. So the first question is what is the point estimate? The point estimate is simply calculated as x bar 1 minus x bar 2. So that's going to be 551 minus 487 64. My pen seems to be writing a little bit off tonight, which is discouraging. Okay, here we go. Now it says construct a 95% confidence interval for the difference between the mean weekly earnings of the two populations. So I'm going to scroll up a little bit so I have room to write. I have all my information up there that I need. I know that my formula is going to be x bar 1 minus x bar 2. That's my point estimate. We're going to add and subtract. It's going to be z sub c, my critical value for my z, multiplied by the square root. Let me double check that. It should be the square root. Yep. Okay. Here we go. Multiplied by the square root of the variance from population 1 divided by the sample size of population 1. The variance for population 2 divided by the sample size of population 2. And all of that, if I can get my pen to write up here, underneath the radical. So I already calculated that the difference here, my point estimate, is 64. So I have 64 plus or minus my z sub c. So let me see here if I can get my z sub c here real quick. And I am doing a 95% confidence, and so my 95% confidence is right here at 1.96. So it's going to be 1.96 multiplied by the square root of 66 squared divided by 500 plus 60 squared divided by 700. And here I'm going to help you track that in. So here's my 66 right here, and here's my 66 right here, my sigma 1. I'm going to square it. And then I have my n sub 1 right here, n sub 1 right there. I have my sigma sub 2 for population 2 right here, and I'm going to square it, divide it by my sample size for population 2, and it is right there. So I'm going to put this in my calculator, and I'm going to say 64 minus 1.96 times the square root of 66 squared divided by, oops, let me go back and put that in parentheses. You should put that in parentheses, guys. So it's going to be 64 minus 1.96 times the square root, put parentheses, 66 squared divided by 500, close parentheses, plus parentheses, 60 squared divided by 700 parentheses, and push equal. So that's going to be equal to parentheses 56.70. And now we're going to add that instead of subtracting it. And our upper bound is 71.30 cents. So it's a 95% confidence interval for the difference between the mean weekly earnings of the two populations. What I want you to notice is that the differences in both of these cases is positive. It's $56 and $71, okay, and 30 cents there. So there's a decimal right there. So this says that since we took the construction worker, going back to our original problem, we took the construction worker's average salary and subtracted the manufacturing. This means that we are 95% confident also that the construction workers make more money than the manufacturers, because both of these values are positive, and they make on average, okay, $56.70 to $71.30 more per week than manufacturers. Let's do another one here. This one here is Betty conducted a management progress study with AT&T management job holders to assess the performance of those who possessed a college degree and those who did not. Refer to the two groups and participants as college and non-college participants. That's going to be what I'm going to refer to them as. The samples include 274 college, 148 non-college participants. In the area of motivation, this is what we're studying, for advancement, in other words, promotions, the mean scores were 2.89 for college participants and 2.7 for non-college participants. We had two standard deviations being 0.57 and 0.64 respectively, and this was obtained from samples. So find a 99% confidence interval for the difference between the mean scores of the two populations in the area of motivation for advancement or promotion. Okay, so because we do not have our sample standard deviation, our population standard deviation, we're dealing with our sample, we're going to be doing a t-test. So let's go ahead and write down everything that we know. We know that we're going to let population 1 be college. We're going to let population 2 be non-college. And we have X bar 1 for college is equal to 2.89. X bar 2 for the non-college is equal to 2.70. We also know that our sample size for college was 274, and we know the sample size for our non-college friends was 148. We know that our sample standard deviation, S sub 1 for population 1, is equal to 0.57, and we know for population 2 that our standard deviation was 0.64. And we're being told that we need to calculate a 99% confidence interval. Okay, that's what we're being asked. Now, because we do not have our population standard deviation, we're going to be using our sample standard deviation. This means that we are going to be on a t distribution. So this is a t distribution. And we're going to be using our sample size for the smaller of the two populations. So our degrees of freedom is going to be equal to, in this case, n sub 2 minus 1, which is going to be equal 147. And we're going to be 99% confident. So let's go ahead and pull up our chart down here. And here's our t-table. So our 99% confidence interval is going to be right here, okay, right here. And we're going to come down to 147, but we know our tables don't go down that far. So is that the second row over? That is the second row over. So we will look at 100 degrees of freedom is what we will use. So we're using tables. So it's going to be 2.626. So 2.626 is what we're going to be using as our critical value for this particular problem. Okay, so our critical value is going to be 0.99, and our degrees of freedom, we really used 100, but we'll put 147 because that's what it was supposed to be, and that is equal to 2.626. Okay, so now to calculate our confidence interval, it's going to simply be our point estimate, which is x bar 1 minus x bar 2 plus and minus t sub c, our critical value, multiplied by our variance for population 1 divided by our sample size for population 1, add it to our variance for population 2
divided by our sample size for population 2. So let's plug in our numbers. So it's going to be 2.89 minus 2.70 plus or minus 2.626 multiplied by the square root of 0.57 divided by 274 plus 0.64 divided by 148. We're going to put this in our calculator and we will find out that our lower bound, 2.89 minus 2.7 parentheses, subtract 2.626 times the square root, don't forget your parentheses here, of 0.57 squared, almost forgot that, there we go, squared, divided by 274, close parentheses, plus open parentheses, 0.64 squared, divided by 148, close parentheses. Our lower bound is 0.0249, and our upper bound, we're going to do the exact same arithmetic, but we're going to instead add the margin of error, which is going to give us an answer of our upper bound of 0.3551. Okay, so here is our 99% confidence interval about the difference between motivational people motivated for promotion of college executive or people with college careers from a college and people who did not have a college education. And based on the fact of how we did our differences, we will be able to say that the people who are employed, who did go to college and receive a college education, are more motivated to receive advancement and promotions than non-college educated. Alrighty, let's look at our next one here. A consumer agency wanted to estimate the difference of the mean amounts of caffeine in 2 brands of coffee. The agency took a sample of 15 1-pound jars for brand 1, and it showed that the mean amount of caffeine in those jars was 80 milligrams with a standard deviation of 5 milligrams. Another sample, which was we took 12, sample size was 12 1-pound jars of brand 2, gave a mean amount of caffeine equal to 77 milligrams per jar with a standard deviation of 6 milligrams per jar. It says construct a 95% confidence interval for the difference between the mean amounts of caffeine in 1-pound jars of these 2 different brands. Okay, it says first off, what is our point estimate? Remember, our point estimate is simply going to be x bar 1 minus x bar 2. Let's go ahead and write down our summary information though. We know that we had a sample size for population 1, brand 1, was equal to 15. We got that right here. And then we know that our x bar for sample 1 was 80, so that's x bar 1 is equal to 80. And then we have our S sub 1 is equal to 5. Then we have our sample size for population 2 was 12. X bar sub 2 is equal to 77. And our standard deviation is equal to 6. It says, what is our point estimate? Remember, our point estimate, because we're doing a confidence interval about the difference, okay? So it's going to be the difference. Our point estimate is going to be the difference of the means. So this is going to be equal to 80 subtract 77. So the difference is 3. So this is our point estimate. Okay, now it says calculate a 95% confidence interval. Again, because I only have my sample standard deviations, that means I'm going to be on a t distribution. Okay, and I'm going to use the smaller of my sample sizes, which is going to be N2 to determine my degrees of freedom. So my degrees of freedom are going to be equal to 12 minus 1, which is 11. Okay, and we want to be 95% confident, so I'm looking for a t.95 comma 11. That is what I'm looking for. So let's come on up here and let's see here. Nope, not that one. So did I say 95%? My memory. Let's see here. Yep, 95%. So we're going to be doing a 95%, which is this right here, 11 degrees of freedom. Looking at the intersection of those two, the column and the row is going to give me 2.201 as my critical value. So 2.201. 2.201. Alrighty. So now let's go ahead and calculate our confidence interval. So it's going to be the difference of the means, which is going to be 3. So it's going to be 3 plus or minus 2.201 multiplied by the square root of 5 squared divided by 15 plus 6 squared divided by 12. So our lower bound is going to be 3 minus 2.201 times the square root, parentheses, 5 squared I know is 25, divided by 15, plus 6 squared is going to be 36, divided by 12. And so my lower bound is a negative 1.75. We're just going to go to 2 decimal places on this one. And then the upper bound is going to be the exact same formula, except for we're going to be adding our margin of error. And that's going to be equal to 7.75. Now, notice that this interval right here contains 0. Do you see that it contains 0? Because it contains 0, I cannot say that one brand of coffee definitely contains more caffeine than the other brand. It would have to not contain 0 like my other confidence intervals for us to be able to conclude that one brand contains more caffeine than the other brand. Very much this is just like a hypothesis test that we've all already started talking about and learning about in class, is when you do a confidence interval, if the interval contains 0, then you have a non-significant test. However, if you have a confidence interval that does not contain 0, then you have a significant test. And you can draw good conclusions off of that and make inferences. Okay, let's look at our next one. Here we go. Confidence intervals about the difference of two population proportions for large and independent samples. So notice this formula and what we're talking about has to do with large and independent samples, and that's it. So we have confidence intervals for P sub 1 minus P sub 2, which is proportions for two different populations. And our confidence interval is going to be given as our point estimate, which is the difference of the two sample proportions, P hat sub 1 minus P hat sub 2. That's going to be our point estimate, plus or minus Z. Remember, with proportion, it's always a Z critical value. And then the standard error about the difference of the proportions. And here's our formula for that right here. Let me go ahead and label this right here. Let's see here. This right here, this part right here, is the point estimate. I
thought I had that labeled, but evidently I don't. Okay, so there's our formula. And it says construct a 99% confidence interval for P sub 1 minus P sub 2, the difference of two proportions from two different populations from the following scenarios. So I have my sample size is 300 for population 1. My P hat for population 1 is 0.53. My sample size for population 2 is 200. And my P hat for population 2 is 0.59. And that is really everything that I need to calculate my my confidence interval about the difference of my two proportions. So first thing I need to do is put down my point estimate. So that's going to be 0.53 minus 0.59. That's my point estimate. Add and subtract my Z, my critical value. I'm doing a 99% confidence interval, and so that's going to be right down here. 99% confidence interval is 2.575. So 2.575, 2.575 multiplied then by P hat 1, 0.53 multiplied by Q hat 1. Remember, Q hat 1 is nothing but 1 minus 0.53. In other words, P hat sub 1 divided by my sample size of 300. We're going to add to that 0.59, that's my P hat 2, multiplied by Q hat 2, which is 1 minus P hat 2, divided by my sample size, which is 200. And all of that's underneath the radical. So let's go ahead and put this in a calculator to get our final answer. So it's 0.53 minus 0.59, close parentheses, minus 2.575 times the square root of parentheses, 0.53 times 1 minus 0.53 divided by 300, close that parentheses, plus open parentheses, 0.59 times parentheses 1 minus 0.59, close parentheses, divide by 200, close parentheses, equals. So I get equals, lower bound, negative 0.1763, comma, and we'll go on up and grab that one. Put a plus sign and 0.0563. And normally I want to go to 6 decimal places on proportion, and I should have just now, but I didn't. So, well, if I'm going to go to 6 decimal places, let's go ahead and do that. So it would be negative 0.1762 99, and then the other one is 0.5, oops, 0. Should be a 0 right there. 0.56299. There we go. So here is our 99% confidence interval about the difference of the proportions. It's going to be negative 0.176299 to 0.056299. Notice again that this interval does contain the number 0. So that means that the difference is not significant one way or the other concerning this interval. Okay, all we can say is that we're 99% confident that the true difference between the two proportions would be contained between these intervals. A researcher wanted to estimate the difference between the percentages. So how do you know when to do X bar versus P hat? Well, percentages is going to be P hat. Means would be X bar. Okay, I have some students that struggle with that. So the differences between the percentages of users of toothpaste who will never switch to another toothpaste. In a sample of 500 users of toothpaste A, taken by the researcher, 100 of them said that they will never switch to another toothpaste. In another sample of 400 users for toothpaste brand B, the same researcher found out that 68 said they will never switch to another toothpaste. We're to construct a 97% confidence interval for the difference between the proportions of users of the two toothpaste that will never ever switch. They are very brand loyal. The first one is, what is the point estimate for the proportions of users of the two toothpastes that will never switch? So when we look at this, we know that we can say that for N1 we had 500 users, and we know that X sub 1 is equal to 100. In other words, 100 people said they will never switch. I use these two numbers to get my estimate of the proportion that will never switch. So it would be X1 divided by N1, which is 100 divided by 500, which is 1/5. Okay, so that's how I get P sub hat 1, the proportion of users that will never switch are going to be brand loyal to toothpaste A. And it's going to be how many people said they will never switch? 100 people said they would never switch. How many people did we interview? 500 people we interviewed. So that ratio gives us P hat 1. Now let's look at P hat 2. First thing I need to know is how many people did we interview for toothpaste B? We interviewed 400 people. So our sample size for population 2 is 400. How many people in population 2 said they will never switch? We have 68 said that they will never ever switch. So to get P hat sub 2, that is going to be the ratio of 68 divided by 400. Okay? And now I'm going to construct a 97% confidence interval. Okay, so what's our point estimate? Our point estimate is going to be 1/5 minus 68 divided by 400. That's going to be our point estimate. Yes, I could have done some reductions of fractions, but I'm not going to worry about it. I'm just going to go ahead and convert it to decimal form. So it's 1/5 minus 68 divided by 400, and that is equal to 0.03. So that is my point estimate. Now coming down to a 97% confidence interval. 97% confidence interval, I don't know if we have that on our chart. I may have to look that up to get RZ. Let's look and see if we have it 97%. I doubt I do. Let's see here. And we don't have a 97. So let's go through the process real quick of figuring out how we get a 97%. So again, to get a 97% confidence interval, our mean is going to go in the center. And because we're doing a confidence interval, we're going to have to put half of alpha on the left tail, half of alpha on the right tail. In this case, alpha is equal to 0.03. How did I get alpha? It's going to be 1 minus 0.97, because that's my confidence level, which equals 0.03. So half of alpha is going to be 0.03 divided by 2, and that's 0.015. So I'm going to put 0.015 in the left tail, 0.015 and 5 in the right tail. In the very center, we know that we have
0.97. So if we were to add all of this up all together, it equals 1.0. So I need to find the negative z value and the positive z value. Those are z's, not 2's. Let me rewrite those as cursives so those look a little bit better. So a negative z value and a positive z value. Okay, and we need to find out what those are. So looking at our tables here, it's 0.015. We're going to come in here. We're going to find the area under the curve, which is 0.015. So we're looking, and we're looking. We're getting close in here. 0.015 right here. It's an exact point. So we come, let's see if I can get the top. I can, look at that. So right here is 0.015. Right there is the area under the curve, where the area to the under the tail is 0.015, which is half my alpha. So I know my critical value is going to be negative 2.17. So negative 2.17. So this is going to be equal to negative 2.17, and this one here then is going to be positive 2.17. Alrighty, so now I know that my z sub c is going to be equal to 2.17. To calculate our confidence interval, it's going to be our point estimate. Our point estimate is right here at 0.03. So we're going to go 0.03 plus or minus our critical value, 2.17, multiplied by the square root. Remember, all the way up here, it was p times q divided by our sample size plus p times q divided by our sample size for each population. Okay, so 1/5 is going to be 0.2. So my p hat 2, or I'm sorry, my p hat 1 is 0.2 multiplied by my q is 0.8 divided by my sample size for sample population 1 is 500 plus, let's see here, 68 divided by 400 is equal to 0.17. So that's nice. It's a nice even number. So we have 0.17 times 1 minus 0.17. That's going to be q, which is 0.83 divided by 400, if I remember the sample size. Yes, it is, for population 2. And all of this is underneath the radical. So my lower limit is going to be 0.03 minus 2.17 multiplied by the square root of 0.2 times 0.8 divided by 500, close parentheses, plus open parentheses, 0.17 times 0.83 divided by 400, close parentheses. And that's going to be negative 0.02628. That's 1, 2, 3, 4, 5, and then a 4. And now we'll go up and grab that, and then we'll change that to a plus sign. And that is 0.00, nope, sorry, that's an 8, 6, 2, 8, 4. It's 1, 2, 3, 4, 5, 6. There you go. Now, proportions are very, very sensitive to rounding errors because we're dealing with such small numbers to begin with. That's one of the reasons why we always go to 6 decimal places when we deal with proportions. The second reason, though, is if I ever want to take and convert any of my proportions to percentages, I would multiply these numbers right here by 100. And if I were to multiply this number right here by 100, the decimal place would come right in here between that 2 and that 6. And if I do that, then how many decimal places do I have left? I have 4 left. And I always want to have at least 4 decimal places when I work with statistics. So that's the second reason why we always do proportion to 6 decimal places. And so our confidence, we're talking about toothpaste, and so we're saying the difference in the proportion between brand A and brand B of users that will never ever switch brands is between negative 0.026284 and 0.086284. And I'm 97% confident of those results, aka if I repeat this experiment 100 times, 97% of the time I'm going to end up with a sample difference between these two values. Okay, I hope you enjoyed this lesson. I hope it was beneficial to you. Have a good night, and let me know if you have any additional questions.